Hello everyone. Today we have a pleasure to host Eric Anschuetz, who will give a talk on enhancing generative models via quantum correlations. Eric is a Sherman Fairchild postdoc fellow at Caltech, having recently finished his PhD under Aram Harrow at MIT. His research focuses on studying the performance of quantum machine learning algorithms, when they are useful, when they are feasible, and when they break. Previously, Eric has shown how techniques from random matrix theory and Morse theory can be used to study the loss landscape of quantum machine learning models. Most recently, he has shown how non-universal quantum resources can lead to expressivity advantages over classical generative models using techniques from quantum foundations research. Okay, Eric, stage is yours.
Thanks. Thanks for the nice introduction. Yeah, as was mentioned, I'm Eric. I'm a postdoc over at Caltech, and my background really is in like quantum computing and quantum information theory. Um, but throughout this talk, I'm going to assume people don't really know any of that, and I'm going to give a lot of background. So don't worry if you see quantum correlations in the title and aren't sure what that means necessarily. But yeah, I'll be talking about work from a couple years ago with a bunch of folks over at Harvard and Ignacio Sirac, who's in Munich, of course, on enhancing generative models via quantum correlations. And the interesting thing about this result is that you can actually phrase it completely in a tensor network language, which is just here we show memory separations between hidden Markov models or equivalently matrix product states with non-negative values for the tensors and normal matrix product states. But the interesting thing is that we actually show the separation using techniques from quantum foundations research. And I'll explain all that in a second. But just to give a very quick rundown of what I mean when I say quantum. Um, so if you took a physics class in high school and you think of like Newtonian mechanics and you have a box of n marbles or something, if you know the initial positions and velocities of these n marbles, and you know physics, like you know how these marbles evolve in time, then you can calculate the state of the marbles at any point in time in the future. You just need to know the initial positions and velocities. So with n particles or n marbles, it grows with n. But in quantum mechanics, so like the physics of microscopic things, particles, whatever, if you had an equivalent system, the degrees of freedom would grow exponentially in the system size. So if you're into chemistry or you ask any chemist, they know this all too well because they spend lots of supercomputer time trying to calculate like ground states of molecules or, you know, complicated protein folding problems and things like that, which, you know, it's difficult to simulate these microscopic systems just because these degrees of freedoms grow exponentially in the system size. But the interesting thing about these quantum mechanical systems is that you can kind of turn this on its head and consider using quantum system dynamics to solve what you might consider are classical problems. So things like factoring large numbers, solving large linear systems of equations, doing unstructured search. These all are algorithms or tasks that you can actually do more quickly if you had access to a quantum system than a classical one in trying to solve these problems, or like a traditional computer trying to solve these problems. And the non-trivial bit is that you can actually digitize this quantum system dynamics to make it a form of computation. So this is what, when you hear quantum computation, what people really mean is like digitized quantum system dynamics to solve problems that we're interested in. Okay. And we're not at the stage of factoring large numbers yet, really, because the quantum devices we have today are very small and very error prone, but they are able to do things nowadays that are beyond the reach of classical computers or traditional computers. So the most famous example, probably a couple of years ago, Google had this result where they had a quantum device, their Sycamore quantum computer, And essentially what they did was sampled from a very complicated probability distribution. And they claimed that this sampling from this distribution was very difficult for classical computers to do. It turned out that eventually people came up with algorithms to sample from this distribution using more traditional computers, but it's still much slower than if it were sampled on this quantum device. So in other words, we're like entering a regime where maybe not quite yet we can solve things like factoring or unstructured search, but we can start probing quantum dynamics and sample from complicated distributions, which if you're interested in generative modeling, kind of points to maybe we can use these devices, or in the future, like less noisy versions of these devices, to sample from complicated distributions that otherwise we would not have access to. And tons of people have thought about this. Like, I'm for sure not the first one to think about this. People have considered quantizing, for instance, classical Boltzmann machines. You can consider thermal states of quantum systems and then show that they are more powerful than classical traditional Boltzmann machines. You can quantize GANs. You can consider quantum versions of essentially like any machine learning model you're interested in. Doesn't necessarily mean they'll work very well, but in principle, you can consider this. And often you can show that these quantum devices can sample from distributions, or these quantum generative models can sample from distributions that are difficult for traditional machine learning models to sample from. But typically, the way the proof strategy goes for these kinds of separations is something like you consider a distribution that just reduces to factoring large numbers, and then you claim that your quantum machine learning model can do this because it can run this quantum algorithm for factoring large numbers. And then you say that factoring large numbers is probably hard using traditional computers, and then that's it. So it's like a very non-constructive way of thinking about these quantum machine learning models, and it doesn't really tell you where you would actually want to use these things, right? Like if you're, if you have a data set that's given to you that's just like classifying discrete logs or something, or factoring large numbers, then yeah, you could use quantum machine learning models. But for like sequential data or anything more practical, like this doesn't tell you anything about what we should be interested in. So the goal, for me at least, behind this work was to come up with concrete constructive proofs of expressivity or memory separations between traditional machine learning models and either quantum generative models, or, as I'll be talking about today, more of a quantum-inspired generative model, so a matrix product state here. And the nice thing about the interpretability aspect, so the fact that this proof is constructive, is it gives more intuition as to where you might expect separations, or like what data sets you would want to use these non-traditional machine learning models. It might give you intuition on how to construct better models. And as I'll briefly talk about at the end of the talk, it actually gives you some intuition on whether or not these models are efficiently trainable, which in the context of quantum machine learning isn't necessarily a given, it turns out. So just to summarize what I'll be talking about over the next 45 minutes or so, what we show in this paper is that there exist distributions that are easy for matrix product states to sample from, but they're difficult for certain Bayesian networks to sample from. And in other words, we show that hidden Markov models, or rather matrix product states, can sample from a distribution that we come up with a given bond dimension, but a hidden Markov model would need a bond dimension that grows super polynomially with the bond dimension of the matrix product state to sample from this hierarchy of sequence distributions, essentially. And I'll give more details in a little bit. And then we give a very constructive proof. So we show exactly why this separation is occurring. And it happens to be because matrix product states can represent certain kinds of correlations that hidden Markov models do not have an easy time of representing. And it turns out this kind of quantum mechanical or quantum inspired correlation is known in the quantum information community. It's something called quantum contextuality, and I'll discuss that also later in the talk. And then very, very briefly at the end, I'll discuss more recent work that extends some of these ideas to neural networks, rather than just showing separations over Bayesian networks, showing separations over things like recurrent neural networks or whatever. Okay. Any questions on the setup before I delve into the results?
I have a quick question. So I'm
Yeah.
always confused when people refer to quantum machine learning.
Mm-hmm.
I mean, what does it mean if you have like a very quick sentence that's...
Yeah, so the annoying thing is, depending on who you ask, it means different things. What I mean here is just one day we'll have these error-corrected large quantum devices, and we already know that there are computational tasks that they can do that are difficult for more traditional computers. And so one research direction that people are pursuing now are whether these quantum devices can be used to implement machine learning models that are difficult for classical computers to implement.
Yeah.
So yeah, for the purposes of this talk, I'll just steer more towards like the tensor network formulation of our results. But another way of thinking about our results is as like a quantum machine learning separation.
Great, thanks.
Okay, and then there's another question.
Yeah, you can
Hi.
keep it for the end if ever. Hello. I was wondering, what's the state of the art for like because you mentioned sampling from complicated distributions
Sure.
with quantum systems. Like, what's sort of like the state of that right now? Does it work? Is it sort of like, can we do it?
Yeah. So we can do it in practice. So going back, these experiments exist. There's a bunch more that I just limited space on the slide that I couldn't, didn't have room to fit. And essentially, though, the issue in terms of coming up with anything practical for sampling from the current distributions these things can sample from is that they're very contrived. So essentially, the distribution being sampled from is, okay, consider uniformly random like operations performed on your quantum computer, and then sample from the like output of this algorithm that you're sampling from, or like this circuit you're sampling from. So it's very contrived, and you don't really expect it to be useful for any reasonable, like, I don't know, maybe there is a use, but I can't think of one. Well, one thing you could use it for is like random number generation in a certified way, it turns out, but I won't get into that. So yeah, you can do it, but what is more unclear is whether you can do this for like interesting distributions or distributions where you might actually be able to model something in nature rather than just modeling itself, essentially.
Okay, yeah, that makes sense. Thank you.
Sure. Okay, pushing forward. So what I'll be talking about over the next 40 minutes is, first, I'm going to give a brief rundown of Bayesian networks. You guys might actually know Bayesian networks better than I do because you're all in machine learning, but I'll give a brief rundown, and then I'll talk about the, depending on how you want to think about it, either the quantum extension of Bayesian networks or a quantum inspired extension, so like a matrix product state extension of Bayesian networks that we'll be considering to show our separation. Then I'll run through our main result. And then I'm going to hopefully give some good intuition as to why our result holds. And to do that, I'm going to have to talk about quantum contextuality, and then I'm going to give a lot of examples to hopefully make it clear what's going on. And then at the very end, just very briefly, I'll talk about more recent results, extending this to neural networks. So, okay, Bayesian networks. So the way I think of Bayesian networks in my head is It was kind of machine learning before machine learning was cool. And what Bayesian networks are essentially ansatz for like the factorization of any given probability distribution. And I'll give an example in a second. But the idea is if you know there's some structure to the correlations in your distribution, you might be able to get away with fewer parameters to describe this class of distributions than if you were just completely parameterizing a very generic probability distribution. And you might be able to run expectation maximization to train these things efficiently as well, depending on your structure. But just to give an example, oops, wrong way. We can consider a distribution over 4 variables that are d-dimensional. And by Bayes' rule, you can always factorize this, right, into like the marginal distribution of y1, y2 given y1, y3 given y1, y2. But maybe your distribution's of the form where y4 is conditionally independent from y1 and y2. So conditioned on y3, it doesn't have any dependence on y1 and y2. And you can just write this factorization equivalently as a graphical model, right, just showing what all these dependencies are. And this is all that's meant when people say Bayesian network. And there's something else I wanted to say about this, but I forget. So, right, you can come up with these graphical models. Oh, right, and this graph should be directed because these conditional distributions, are directional, right? It's y3 conditioned on y1, y2. So you write arrows going into y3 from y1, y2. And then it should also be acyclic because by Bayes' rule, you're not going to have multiple p of y2s, for instance, in this factorization. So it's going to be acyclic. So has been known actually for a while now. You can just rewrite any Bayesian network as an equivalent tensor network. And I wrote it in a very strange way. And this comes from thinking about it as like a quantum circuit or an operation run on a quantum computer. But really all you should think of this as is these u's and t's are essentially the square roots of those factors that we saw in the previous slide. But I'm going to go more slowly. So these zeros here, just think of them as some fixed vector that's being contracted in this tensor network. These y1, y2, y3, y4, these are just projectors onto that entry of yi. So, if y1 equals a, it's just a projector on AA, essentially. And then when contracted with this vector, this u1 is essentially just the square root of that marginal distribution for p1. And then the t's are a bit stranger, but essentially this is just a block diagonal form of these other conditional distributions. So each block corresponds to every possible value for these conditions. And then what that block is just like u, where it's the square root of that distribution. And in the context of quantum computing or quantum information, these are called uniformly controlled gates. But you can just think of them as some block diagonal form where each block is the square root of the distribution we're interested in. Okay, I'm going to go slowly because that was a lot. Are there any questions on this?
Just very quickly to make sure I got it, like this tensor that you represent with the diagonal line is like the copy tensor, like this diagonal, hyperdiagonal tensor with like the small ones, right?
I see this. Yeah, so I was a bit sloppy with notation. This is really really the two diagonal lines should be considered as like one tensor that just block diagonalizes this thing.
And so is it
Yeah, this is really a quantum circuit notation. So,
okay,
yeah,
but does that correspond to the Kronecker delta, or is it something different?
No, it's something different because,
okay. Thanks.
For instance, this A and this B can be different.
Okay, I see.
Yeah.
Okay, thanks.
Yeah, I was just sloppy with notation. Okay. Any other questions? Okay. So I apologize, but this is the first introduction of something quantum computation-like in this talk. But just for brevity, I'm often going to write these tensor networks in a quantum circuit notation. So given you don't really have to understand like what this picture is, but this is just like the square root of this diagram, right? Like this is just this left half. I'm just going to write it like this for brevity. But if you see this, just think of the tensor network version as this y1 then becomes a projector onto y1, and then you flip it and then contract it together. But generally, when you have a tensor network, you can rewrite it as a Bayesian network when those single node unitaries or orthogonal matrices, it turns out it doesn't really matter. And these uniformly controlled gates are arranged in a way that they form a directed graph, and also if they're acyclic. So in other words, if we go back to this picture, we could have a more general, setting of these uniformly controlled T tensors, and it would still represent a Bayesian network as long as this still formed, like the connectivity of these T's were still a directed acyclic graph. Does that make sense? Because, as long as this is a directed acyclic graph and these actually represent the square root of some probability distribution, we can just rewrite it like this, where this is now the connectivity structure.
I have a general question, probably a naive one. So I'm always confused when we say like probabilistic graphical models are equivalent to tensor networks. It means the discrete version of the probabilities. So the tensors are like there when you had P of C given A and B. For all possible values of A and B in your tensor, you have this probability.
Yeah.
Okay.
So it's not a very efficient representation because it grows exponentially with the number of controls you have.
But if do you have any way to discretize A and B, like sampling where A and B coming from, or you are not concerned about this?
Yeah. So here we're considering Bayesian networks over like discrete variables.
Okay.
So it's already discretized.
I see.
At the very end, I'll talk about if you have continuous variables. And there you can say essentially equivalent things to what I'm saying here, except over classes of neural networks rather than classes of Bayesian networks.
I see.
But it's a very similar idea, it turns out.
Thanks.
No problem.
I also have a quick question. When you say the tensor network is a DAG, you mean where is the direction in the tensor network?
So
there exists...
this is asymmetric. This is blocks of this T with the blocks labeled by this A and B. So this is the direction, this uniform control, where essentially previous wires or previous lines dictate what block this thing should be in. Yeah, June?
Yes, so I would like to comment on the control nodes. If actually the control node is actually the copy tensor. If you look at the mathematical format you show in here, if you look at like for example for the 2-qubit control gates you showed here, if you look at the mathematical format, you have the projection from A to A and the tensor TA. So I'm looking at the 2 qubits. Yes.
So for this one I agree. Yeah, it is. This bottom one, it isn't, though. It would be if you had this go directly to T, I guess. The issue as written is that if this were a copy tensor, this and this would have to be the same, but we're summing over distinct A and B.
Okay.
Yeah. So I was just sloppy with notation. Sorry. Okay. Okay. Cool. So we're gonna move on from this. This is just a tensor network way of writing a Bayesian network. And what we consider in our paper, okay, coming from a quantum computing background, we call it a minimal quantum extension of Bayesian quantum circuits. What you can also think of it as is just the simplest addition you could possibly have to your tensor network. All we're doing is right before the projector, we're adding an extra unitary that's being contracted. But this unitary is completely local. Naively, it's not giving any correlations between these links because everything is acting locally. It's just changing essentially what basis this projector is projecting onto. So going back to this picture, what we're doing is this projector is now going to be sandwiched between V and V dagger, which are unitary matrices that are transforming the basis of this Y projector. Okay? So now this doesn't necessarily represent a Bayesian network. I mean, for one, this unitary can have complex numbers and stuff, or it can have negative numbers. So this contraction is definitely not a Bayesian network anymore, but it's obviously also not just a generic tensor network contraction. It's a very slight upgrade from this formulation here. So we call it basis enhanced. Again, this name comes from quantum computing setting, but you don't have to worry about it. All we're adding to the original definition is, okay, we still have to have a directed acyclic graphical structure for our T matrices. It's just that right around the projector, we're allowing for a change of basis, or a unitary conjugation of this projector at the end. Okay, yeah, question.
Yeah, very quick question. So here I was wondering, you don't enforce any positivity onto the quantum? You say a quantum circuit is Bayesian if those two conditions hold, but you're not asking that the tensor are actually positive, but somehow you get back positivity by the fact that they are acyclic.
Right. So that's not obvious. It actually comes from the fact that you don't have this V here. Mm-hmm. If you don't have this V here, and this is signed, okay, going back to this picture, mm-hmm. It turns out, okay, if you look at the lines here,
yeah,
this is, depending on the signs, just a sum over some complex phase times the square root of the probability at that entry of the vector. But when you contract it with this other half, that sign gets complex conjugated away, essentially, or it gets squared away. So it turns out, yeah, you can, for simplicity, just make everything positive, but it turns out not to matter. It will matter, though, when you have a unitary here, mm-hmm. because then it doesn't necessarily get complex conjugated away or squared away.
Interesting.
Yeah, so thanks. The way to think of it from a quantum computing standpoint is Z operations don't matter when you're doing a measurement. But yeah, that's a quantum computing way of thinking about it. Okay, so we have this thing now, basis enhanced Bayesian quantum circuits. And this is what we're going to use to prove our main result. And to explain how that goes, I'm going to take a step back and talk about the task we're actually interested in, which is sequence modeling. And in particular, solving a translation problem. using hidden Markov models, and then this basis enhanced version of them, which it turns out is an MPS. So, okay, what's a translation problem? You're given some input sequence X, and you want to give any correct translation of this sequence into another sequence Y, where correct, depends on the problem. So as an example, if I'm trying to translate from Spanish to English, maybe I should have used French to English for this talk, but Spanish to English, I could say me llamo Eric. And of course, translation isn't one-to-one. There's like a million ways of translating me llamo Eric into English. So you could say, my name is Eric. You could say, I call myself Eric. These are all, the same, essentially. And for a translation problem, we're not really interested in all possible translations of an input sequence. We only care about giving one correct one, So let's say our model outputs, I call myself Eric. So given a conditional distribution, if we're trying to model it, essentially what we want is a finite backwards KL divergence with the uniform distribution over correct translations. So in other words, to say it more simply, maybe, we want our model to output a translation that is a correct translation. So we want the support of our model over what it spits out to be contained in the support over correct translations. So this isn't necessary for the rest of the talk, but this is the error model we're considering. So like whether or not you achieve even a finite KL divergence on this distribution. And before RNNs and transformers like completely took over, the way to do this classically or using traditional methods was to use a hidden Markov model. So this is just a Bayesian network. These nodes on the upper row you should think of as containing x1, x2, x3, x4. And these green nodes are latent variables to your model. So, it's like the state vector or the latent variable for a recurrent neural network. It's the same kind of idea, except here it's a discrete variable that takes one of D values or something. So what you do is given an input for a given time step and your previous latent variable, you sample a new latent variable, and then you sample from that time step's output given your latent variable. Okay, so this is just a way of like an ansatz for your translation problem. And the more latent variables you have, so the bigger the state space for this green variable, essentially the more memory you have. Because if you have a huge, if your memory is like exponential in the problem size, you can just explicitly memorize everything you've been told. So, with a large enough lambda, with a large enough dimension of lambda, this thing should be able to do everything. But what we want to bound is like, what's the minimum dimension of your state space needed to solve this problem up to that error model I was talking about previously. Okay, so this is really what we're interested in. And we can consider the basis enhanced version of this thing. And yeah, so what you get out is essentially an MPS, or it is an MPS. So on the right here, this is the tensor network you get by doing this basis enhancement procedure. This is from the paper, so the notation's a little different, but this UP is like the U from the previous slide. UT is like T, and UO is like V. And you can just contract along these rows, right? And then have your free indices sticking out that are where M1, M2, and M3 are. And this basis enhanced HMM is just an MPS with a squared overhead in bond dimension. Does that make sense? Like when we contract along these rows, we can combine these two legs into one bigger one that's squared the size, and then this is just an MPS. So, okay. What we show is that this MPS with a bond dimension m or m squared, doesn't really matter, can represent a distribution perfectly. So this conditional distribution perfectly. But a hidden Markov model would need at least m to the log m hidden states per time step. An omega got eaten by LaTeX here. Should be m to the omega log m hidden states per time step to represent. So in other words, there exist distributions that you can efficiently represent with an MPS with bond dimension m squared, but any hidden Markov model would need bond dimension m to the log m, which is more than polynomial. So it's like a big separation. Okay, any questions on the main result?
Very quick question. Is this, it seems that this is independent to the fact that, so HMM, they are like, when you see them as tensor network, they are kind of uniform tensor network, right? You have the same core tensors at each time step. They are like translation invariant system, but is this actually some crucial part of your contribution, or is it it's very, okay, I see.
Yeah, it doesn't need translational invariance. It actually turns out our MPS is translationally invariant. So you could even say a stronger result, which is translationally invariant MPSs can represent distributions that any hidden Markov model, even if it isn't translationally invariant, they need this super polynomial blow up bond dimension.
Okay. Good. This is interesting. And do you know how like in this blow up that you have, the sequence length is not intervening, right? But is it
so the sequence length is log m. Yeah, log m.
Okay. So it would, if you start to do that for arbitrary like sequence length, maybe this would actually play a role in the blow up. Like the larger the sequence, the higher the blow up.
Yeah, in principle, I don't think our results would be able to pick that up though. But yeah, it could be the case that this is an even bigger separation if you go to longer sequence lengths. But at least with our techniques, okay, you can get like m to the any constant you want log m essentially, depending on your sequence length. So yeah, but it doesn't change the overall story here.
Okay, thank you.
Sure. Okay. So I'm going to give the intuition behind how we prove this now. Okay. So to do that, I have to talk about quantum contextuality, which is a very strange phenomenon in quantum mechanics, which essentially is the fact that in quantum mechanics, if you have some measurable observable, so like the magnetic field in a quantum system, it doesn't have a definite value. So it's not like if you're measuring magnetic fields and electric fields in a system that you can just keep track of what all these values are in like a classical memory and then update them as you evolve to like simulate the quantum system, which is very weird. I'm going to give an example, but it's very relevant. This was awarded the Nobel Prize in physics last year for an experimental demonstration of this. So it's very relevant, but it's very weird. I'm going to give an example. So without diving into the quantum mechanics at all, just take my word for the fact that there exists measurable properties of quantum systems. And I'm just going to label these various properties as Q11, Q12, Q13, these Q numbers. And they satisfy some parity relation. So, if you measure anything along the rows and you take their product, you'll always get +1. And then same with the first two columns. But then this final column, if you measured Q13, Q23, Q33, you would get -1. And, you can just experimentally see this. These QIJs are, it turns out, like magnetic moments of particles, but it doesn't really matter. And you can ask, okay, can classical variable assignments do this? Like, is it just that these QIJs are just classical numbers that we're measuring and then happen to satisfy these parity constraints, or is something weirder going on? So we can try and classically assign values to these variables. We can do a very dumb first attempt and give everything +1, which obviously breaks this parity constraint. Then we can try and fix it, but then it breaks this parity constraint. And we can try and fix that, and then we break this one. And so it's straightforward to see that you can't actually like assign classical values to these observations you're making in your quantum system. And to give like more intuition about what is going on here, in other words, say we did give classical values to 8 of the 9 things. If we were measuring along the row and say we got +1, +1, the value of Q33 by this parity constraint, if we were to measure it, it has to be +1 because of this parity constraint. If we measured the things along the column though and got +1, +1, the value of Q33 has to be -1. So by this parity constraint. So in other words, the value of Q33 depends on the context in which it's being measured. If it's being measured in this row context, its value is +1. And if it's being measured in this column context, its value is -1. So this is very weird, but in other words, in quantum mechanics, you can kind of have these context-dependent values for variables that just kind of, it comes naturally. It's not like you have to explicitly memorize what context you're in. If you just do it in a quantum mechanical system, if you just measure these things, Q33 will naturally have this context-dependent property. Okay? So that's a very high-level overview of this phenomenon, but hopefully that gives you an idea of where we're going to go with this. We're going to construct a translation task that essentially are just classical descriptions of these things you can measure, these observables. And the translation task we're going to consider is very ad hoc and constructed, but essentially it's just, okay, if you were to measure these things in a quantum mechanical system, what are the measurement results you get if you just keep measuring these things over and over again? So the Y are the possible measurement results you can get when measuring these things in a quantum mechanical system. And it turns out, I'm not going to get into this, but you can do this with this basis enhanced HMM. You can simulate this with an MPS where the bond dimension is exponential in the system size that you're simulating this on, but it turns out that will be good enough for our separation. Okay. To reiterate, we're considering a translation task that's essentially completely inspired by quantum mechanics. And we show in our paper that a matrix product state can simulate this translation task because this matrix product state can simulate a certain kind of quantum circuit that can do this. Okay, that was a lot, so I'll stop here for questions briefly. You're muted. Yeah.
A quick question. What was a translation task?
Yeah, so the translation task is sample from this conditional distribution where your X, so the thing you're conditioning on, describes essentially the things in this table. So these QIJs have classical descriptions, like this is the magnetic moment in one direction, this is the magnetic moment in another direction of particles in a box or something. You can just classically write this down. And then what we're translating this to, or rather the conditional distribution we're sampling from, are what you would get when measuring the values of these objects in a quantum mechanical system. So in other words, the translation task is like simulate quantum mechanics for this constrained system.
Okay, so going back to your previous slides, we had two probability distributions, like P of model y given x
Sure.
is this new thing that you're talking about, which is this P of model y given x is what the quantum contextuality model will model, right?
Yeah, so the P of y given x is our data distribution.
Okay.
And P of y given x is essentially in a quantum mechanical system, if you do these measurements, what's the probability you got these measurement results when measuring it? And it will turn out, because of quantum contextuality, this P of y given x is very non-local correlations. Like what you measure early on can significantly impact what you're measuring later on. And it turns out it's because you're constrained by these like parity constraints, essentially, that can act over arbitrarily long distances in your model. So it's a very, we essentially constructed this constraint to give these very non-local correlations, which intuitively a hidden Markov model will struggle with, because it would have to keep memory in the model to keep track of all of the contexts that have been, that it could possibly be in throughout the sequence. And then P model, it turns out that you can construct an MPS where P model is exactly equal to this distribution. And then we're going to show that any hidden Markov model with bond dimension less than this m to the log m, it will have to get a translation incorrect somewhere. Like it just doesn't have enough memory to remember all of these contexts, and it will screw up somewhere. Okay. That's the idea.
I see. Thanks.
Sure. Okay. So, right. Without getting into the quantum, there exists an MPS that can do this. And then roughly at a hand wavy level, any classical model, so like a hidden Markov model, like I mentioned, requires an extra hidden state in it anytime you have this contextual property. In other words, if you have a sequence where you're measuring Q31, Q32, Q33, or you could have a sequence where you're measuring along the column, a hidden Markov model would need to keep both of these prior sequences separate in memory, because if it were to then get a question, which is, okay, what's the value of Q33? Its value completely depends on what was previously measured. So every time you have this phenomenon happening, your classical model will need a separate hidden variable to describe the system. So what we've essentially done is reduce the problem to just counting how many times you get this over the sequences we're considering. And I don't have a lot of time left, but just very briefly, what we show is that, okay, we consider systems where the number of inputs you have grows as 2 to the v squared over 2, where v is the size of the quantum system you're considering, like that governs the size of the translation task. And essentially, this phenomenon occurs every 2 to the v squared over 4 inputs you could possibly have. And you can divide these two things, and you get m log m, m to the log m scaling for the number of hidden variables your hidden Markov model needs to simulate this. Okay, I'm going to skip that. So I know I breezed through the proof at the end, but the idea is quantum or quantum-inspired models can efficiently store this kind of long-range correlation by using quantum contextuality. And in the case of matrix product states, it's because they can simulate this phenomenon with less overhead than a hidden Markov model. Or if you had a quantum device, it could just naturally do it. And so something that's come out of this more recently is searching for other kinds of models where this can happen. So very, very briefly, this is a more recent paper. that looks at this, except instead of looking at quantum contextuality giving advantages over Bayesian networks, looking at it over neural networks. So, like I mentioned, people have been interested in using quantum devices as generative models, essentially by parameterizing whatever operations you're performing on your quantum device, and then sampling from the output at the end. But it turns out generically, you can't actually do this without getting into any details because of lack of time. You have this untrainability phenomenon where essentially the more powerful the quantum model you're considering is, the less trainable it is. So it takes more time to train, the more powerful your quantum model is. And so because of this, if you're interested in actually running a generative modeling experiment on a quantum device, you would want essentially the minimal quantum extension of a classical neural network so that you avoid these training issues, but you still have the ability to do things that classically is difficult to do in a generative modeling setting. Yeah, June?
Yes, so it's the training issue because of the Bayesian plateaus, the gradient
Yeah, so
or...
yeah, that's part of it. Bayesian plateaus occur when it's, yeah, essentially too expressive. You can also have poor critical points. So that's what this plot is from. It's looking at the density of local minima as a function of loss function value. And classically, you often see this like beige line, essentially, in terms of all of your local minima are concentrated at your global minimum. But in these quantum neural networks, when you are in the very generic setting where you're running essentially arbitrary quantum circuits to parameterize your quantum neural network, you're in this setting where your minima are terrible. So yeah, there's a bunch of things that can go wrong. This plot is just me plugging my own work, which looked at minima, but Bayesian plateaus is another way things can go wrong. So yeah, I just want to briefly mention this other result, which is that if you do the same procedure where you essentially are basis enhancing classical RNN, you can say something similar where you can show that this quantum version of a recurrent neural network can perform some translation task that a very wide class of classical neural networks needs memory quadratically larger to perform. And what I mean by classical neural networks, this includes things like transformers, RNNs, LSTMs, GRUs. Essentially, any time you have like a memory bottleneck, this lower bounds how much memory you need through that bottleneck. And this is like an extension of these Bayesian network results to the continuous setting where everything is real valued instead of discrete valued. Okay, so I just wanted to mention that really quickly. And you could do some numerics on like standard tasks and then show a separation. Also numerically, not just through proof. Okay, so where does this leave, this research direction? Something we don't have yet that would be nice is a way to look at sequence data, for instance, and then see if it is amenable to this quantum or quantum-inspired representation. So in the papers I mentioned today, all we showed is that there exists a distribution with long-range correlations that is nicely represented by these quantum or quantum-inspired models. But it was also very constructed. Like it literally came from a quantum setting, and then we just wrote a classical description of it and then made a translation task out of that. So ways to look at real data and then see if it's amenable to this without just having to run your quantum or MPS model on it would be nice. Yeah, just seeing how generically true this is over a variety of data sets. Considering, in the Bayesian network case, what this showed is that MPSs give are more efficient at representing certain distributions than hidden Markov models. But we don't really have something similar in the neural network setting. We technically have a quantum-inspired classical neural network that has separations, but for reasons I won't get into, it's kind of messy. So considering that in more detail would be nice. And then thinking about experimentally implementing some of these quantum or quantum-inspired representations would be nice. So I know I breezed through the end, but thanks for your time. And yeah, feel free to ask questions.
Thanks, Eric. That's great.
I have a couple of questions. Thanks for the talk, Eric. It was really, really interesting. So I have a first question, which is about the core of so the separation result that you get in the end with the Bayesian network and the MPS.
Mm-hmm.
Does it has to do with the fact that now you have complex value rather than positive, or does it has to do with the ANs, like the basis ANs part of it, or how those two related basically, right? So because you started by saying basically we have classical HMM, and now when we move to tensor network, we are doing complex weight, and this complex thing is related to contextuality somehow. So can you, if you'd like to summarize, like
so yeah, you're spot on. Like I mentioned before, when you have this tensor network representation of a Bayesian network, you don't have any signs, right? Like everything is positive, or even if it isn't positive, it's equivalent to if it were positive. So you don't get any so-called interference effects. So these probabilities are just what they are, for an MPS, or in our setting, when you add this final unitary here, that allows you to have an interference effect, because now you're summing these and taking subtractions of these square roots of probabilities. And then that is what is being squared and normalized. So they're kind of, maybe not equivalent, but this final unitary is exactly what gives you the interference effect that then is what ends up giving the separation. So in other words, it's not like we're adding any extra explicit correlations here by adding more of these T tensors. All we're adding is the ability to add and subtract these values, and then that is enough for our separation.
Yeah, that's interesting. Yeah, because there is a lot of things that can somehow come with one another here. Like also the difference between when you take classical HMMs, you can see them as matrix product state, where you're just taking the output of your tensor as the probability, right? There is no Born, there's no squaring thing. So this is also another part of it, right? Whether you take your tensor network and interpret it as a probability, or you take the square and then do your low complex values and stuff. All of this.
Yeah. So here, for instance, okay, maybe I'll go back to here. Pretend you don't have this UO tensor. Then it's just, this is also an MPS representation of a hidden Markov model. Again, if you contract without this UO tensor, just contract along the rows. And it turns out you can actually go the other way as well, assuming your MPS is properly normalized and it's got non-negative values for its matrices. Mm-hmm. You can do an SVD and then rewrite it as an HMM. So another way of stating our separation is we give super polynomial memory separations between matrix product states and matrix product states with non-negative values. So this is another way of kind of saying, really it's the interference effect that's giving us the separation here.
But there was already a result like this, right? Also from Inicio's group, like the...
from Jens Eiser and Sirac, is that the...
Yeah, I think Ivan Glaser and this Nerip's paper.
Exactly. So there they essentially just give an example of how these two bond dimensions can be different. But what we do is we quantify that and we show it has a super polynomial scaling. So yeah, that's another way of stating our results.
I see. Okay, awesome. And again, another question, which is, in the end, this is still a result about MPS, so classically efficiently simulatable system, right? Like.
Oh yeah, so you're asking what's quantum about it?
Not necessarily what's quantum about it, but what insight does it give you about a potential quantum advantage in terms of now if you have some quantum hardware, because now it seems, like when it's very interesting, this result about MPS, but it's not telling us that there is something that we cannot do classically that we should be able to do better on a quantum device.
So this is getting into this result more. So in this paper, what we do is we show, essentially we just consider the continuous variable version of what we previously considered. And there does exist a polynomial time classical simulation of our quantum model here. But something that we're working on and trying to finalize is essentially constructing a hierarchy of these quantum models that get more and more complicated, so that if you tell me a polynomial separation that you want, versus on, to implement it on a quantum computer versus on a classical tensor network or a classical simulation, I can give you the model that achieves that separation. To put it another way, for everything I've talked about here, there are efficient classical simulations, but I can make it as arbitrarily not efficient as you want. At least in the extension, this isn't out yet, but what will be an extension of this?
And this model, like in this hierarchy, those you can make it as complex as possible classically, but still efficient to be done on an actual quantum device.
Yeah. The tricky bit there is you still want it to be, going back to this, you also still want it to be efficiently trainable. And it turns out that's kind of what breaks. So as you go up this hierarchy, the training time also scales polynomially, but gets bigger and bigger. And so really what it is like a quantum advantage during inference. So after you train it, or in other words, if you had this classical simulation algorithm, there's a way, if you consider this quantum-inspired classical model, after you're done training it, you can compile it to a quantum computer and then run inference with like n to the k advantage for any k you wanted.
That's pretty
That's
cool.
Like the idea.
I think I would have follow-up question on that, but I will let others ask questions.
Feel free to email me after. Any other questions?
If not, I'll let you guys share.
It seems that there is no question. Thanks so much, Eric, for the great talk.
Yeah, thanks for having me.
Yep.